What we've discovered is the heaviest known neutron star. It's what's left over after a more massive star ends its life in a supernova explosion. Certain neutron stars emit radio waves. We call these stars radio pulsars. And they spin around kind of like a lighthouse. Every time their beam passes by us, we see a burst of radio waves.
The pulses come in at a very regular rate. And essentially, if there are other things going on out in space or out at the system, those pulses stop being so regular.
And this lets us determine with very high accuracy how that star is moving.
The pulsar that we were observing exists in a binary, so it orbits another star, and that other star is a white dwarf star, which is also a very compact object. So the fact that this object is very compact means that it actually distorts the space-time around it, and it makes it very curved.
And so as this pulsar is orbiting this other star, we see the pulses being delayed as they go past that star. And this delay is known as the Shapiro delay from Erwin Shapiro, the guy who discovered it with radar observations back in the 60s. As long as we have enough precision and can measure time these pulses with enough accuracy and precision, we can see the signature, and that's exactly what we did in this case.
The delay in time that's needed for the pulse to go around the white dwarf is described by Einstein's theory of general relativity, and from that theory we can actually then deduce the mass of the white dwarf star. And by knowing the mass of the white dwarf star and furthermore the inclination angle of the binary orbit, we can then infer the mass of the neutron star. And what we measured was that this neutron star is actually very massive compared to the previous measurements of other neutron stars. The neutron star turns out to be 1.97 plus or minus 0.04 solar masses, so about 2 times the mass of the Sun.
Until now, we weren't sure if it was possible for neutron stars to become much more massive than about 1.4 times how massive our Sun is. This new result, which is about twice as massive as our Sun, has a lot of implications for what exactly the neutron stars are made up of in the first place, what's inside them.
To construct a neutron star that has about twice the mass of the Sun, you need to somehow describe this object physically, and what is it made out of? And there are various different theories or equations of state of how to describe the interior of these stars.
A neutron star is called a neutron star for a reason. We think it's mostly made up of neutrons, which are basic particles that you would find in an atomic nucleus. A neutron star is sort of like an atomic nucleus, except it's about 10 kilometers in radius. There have been theories that inside the neutron star there also exist other new exotic kinds of particles with fancy names like hyperons or boson condensates or kaons or free quarks. And what our measurement is showing is that actually a lot of those theories are not in fact possible. We've ruled out a lot of the theories of exotic particles inside the neutron star interior.
The way that we describe the interior of these neutron stars must now change, that we've made this very accurate measurement of 2 solar mass neutron stars.